This video is about Thévenin's theorem. Thévenin's theorem states that any linear circuit can be modeled as a resistor in series with a voltage source. This allows considerable simplification in the modeling, analysis, and especially design of electric circuits. Thévenin's theorem allows us to model a complicated circuit as a very simple one that has the same voltage-current characteristics at its terminals. This is particularly desirable during system design. For example, suppose we have two circuits interconnected at two terminals, as shown here. We'll call one of the subcircuits circuit A, and the other one we'll designate as the load. We want to design the load circuit. Since the load circuit ultimately depends on the behavior of circuit A, we need a model of circuit A in order to design the load circuit. Design is always iterative. We generally try out different ideas for a design and modify them as necessary to make them work. This makes having a simple model of circuit A extremely desirable. Thévenin's theorem allows us to model a very complicated circuit as a voltage source in series with a resistor. The only requirements are that the circuit is linear and that there are no dependent sources in either circuit that depend on the other circuit. Keep in mind that the replacement of circuit A with its simplified model is a conceptual change used only for analysis purposes. We're not changing the physical circuit itself. Thévenin's theorem depends on representing the circuit as a two-terminal network. The terminals we're going to select are those that interconnect the circuit with the load. What we're modeling are the voltage-current relationships at these terminals. If we come up with a simple circuit that has the same voltage-current relationship as the original circuit, we can use the simple model to analyze the behavior of our load circuit design. To find the voltage-current relationship at the terminals, we can use the same trick we did before, which is to connect a hypothetical current source across the terminals. If we calculate the voltage resulting from this current, we can get the desired IV characteristic. In order to do this, we'll use the superposition principle. That means that the circuit we're modeling has to be linear. Recall that in superposition, we examine the effect of each source individually and then sum up the contributions from all the sources. Our first step then will be to determine the voltage due to this current source I, which I'll call V1. To do this, we kill all of the sources inside circuit A, which leaves a purely resistive network. The equivalent resistance of this network is called the Thévenin resistance, which is represented as RTH. Ohm's law says that the voltage, V1, due to the current source is simply this Thévenin resistance times the current. Next, we determine the voltage across these terminals due to the sources inside circuit A, with the current source outside the circuit killed. Killing a current source converts it to an open circuit, so the current at these terminals is now 0. I'll call this contribution to the terminal voltage V2. Keep in mind that during this step, all of the sources inside circuit A have been restored. Since the terminals are open-circuited, the voltage across the terminals from this step is commonly called the open circuit voltage, which is referred to as VOC. The final step is to superimpose the contributions from the previous two steps. The resulting expression for the voltage across the terminals as a function of the current into the terminals is this. The voltage due to the external current source is RTH times I, and the contribution due to the sources inside the circuit is VOC. This equation can be represented by a circuit as shown here. The voltage across this resistor is RTH times I with this polarity. KVL around this loop says that V is equal to VOC plus RTH times I, which agrees with our desired equation. Creating a physical circuit that implements a given mathematical operation is known as realizing the equation. The hypothetical circuit is called the realization of the equation. Ultimately, Thévenin's theorem says that any linear circuit can be modeled as a voltage source in series with a resistance. Mathematically, the voltage-current relationships across the terminals of these two circuits are identical as long as RTH and VOC are chosen correctly. The resistance, RTH, is the resistance seen across these terminals with the sources in the circuit killed. The voltage, VOC, is the voltage that would be measured across these terminals if the terminals are open-circuited. The voltage-current relationship is the form V is equal to VOC plus RTH times I. There are some conditions for Thevenin's theorem to be applicable. First, since we use superposition in the derivation, the circuit must be linear. Secondly, neither circuit A nor the load circuit can contain dependent sources that depend on voltages or currents in the other circuit. So circuit A can't have any dependent sources that depend on values in circuit B, and vice versa. The voltage-current relationship resulting from Thevenin's theorem is V is equal to RTH times I plus VOC. If I represent this equation graphically, it looks like this curve. VOC is the terminal voltage when the current is 0, and the slope of the curve is the Thevenin resistance seen at the terminals with the sources in circuit A killed. This is a general voltage-current relationship to model any linear two-terminal network. VOC in this relationship is the voltage across the terminals if the terminals are open-circuited. RTH is the equivalent resistance seen at the terminals of the circuit with the sources in the circuit killed. Now let's do an example of determining the Thevenin equivalent circuit seen by this 1 amp current source. After finding the appropriate Thevenin circuit, I'll use that circuit to determine the voltage V1 across the source. The goal here is to treat the current source as the load and the rest of the circuit as circuit A. That means that we remove the current source and find a Thevenin circuit with the same voltage-current characteristics at these terminals as the remaining circuit. Basically, we're going to replace the circuit in the black box with an equivalent circuit consisting of a voltage source in series with a resistor. To do this, we'll find the voltage across these terminals if the terminals are open-circuited and the equivalent resistance at these terminals with any of the remaining sources killed. Keep in mind that these two things are separate problems and don't depend on one another. First, and rather arbitrarily, I'll calculate the Thevenin resistance RTH. To do that, I kill my source, so I leave this 4 ohm resistor. A voltage source becomes a short circuit. These are the terminals I'm interested in. So RTH is the voltage-current relationship across those terminals. And I need this 4 ohm resistance as well. These two resistors are in parallel. So RTH is 4 times 4 or 4 plus 4. So RTH is equal to 2 ohms. Now I'll calculate the open circuit voltage. I replace my voltage source, so I get my sources in circuit A back. These are the terminals I'm interested in. Now it's important to keep in mind that this is an open circuit voltage, so this current is equal to 0. These terminals look kind of like these terminals. But in these terminals, it's not an open circuit. We're finding a relationship between voltage and current, so we don't assume that the current is 0. In this case, current is 0. Let's do nodal analysis at node A. This is 0 volts. This is a dependent node. It's 8 volts. So VA minus 8 volts over 4 ohms. Plus this current, which is VA over 4 ohms, is equal to 0. Multiplying through by 4, I get 2 VA is equal to 8, or VA is equal to 4 volts. From my nodal analysis, VA minus 0 is VOC, so this is also VOC. Next, I'll draw the Thevenin circuit, replace this source, and determine the voltage V1 that I originally wanted to find. Now I'm going to use the Thevenin equivalent circuit I created before to calculate this voltage V1 due to a 1 amp source. So my Thevenin equivalent circuit was the circuit seen by these terminals. So I had a 4 volt source and a 2 ohm Thevenin resistance. Now these two terminals have the same voltage current relationship as these two terminals. If I want to find V1 with the current source in place, I connect that current source across these terminals and calculate the voltage here. If 1 amp is going in here, that means that this voltage is 2 volts. Then KVL says that V1 is equal to 4 volts plus 2 volts, which is 6 volts. The nice thing about having this Thevenin equivalent circuit is that I can very easily assess changes in this load circuit. So if I want to find the effects due to a 2 amp source, I can keep the same Thevenin circuit, 4 volts, 2 ohms, and connect a 2 amp source up to this. Now the voltage across the source, V1, will be 4 volts plus 2 amps times 2 ohms is 4 volts, so that becomes 8 volts. Thevenin's theorem, the ability to represent a complicated circuit as a voltage source in series with a resistor, is one possible way to model a linear circuit. Another approach is to model the circuit as a current source in parallel with a resistance. The latter approach is called Norton's theorem.